Hi everyone, welcome to my talk. I'm Zhihao Tang from Shanghai University of Finance and Economics. Today I will talk about fully online matching, beating ranking and water filling. This is a joint work with Zhiyi Huang, Xiaowei Wu, and Yuhao Zhang. As you can see, I've colored the title into 3 different colors, and this is going to be the 3 parts of my talk. So first, I will introduce our model, fully online matching. This is a generalization of the classical online bipartite matching problem by Karp, Vazirani, and Vazirani. This is proposing an earlier work of us. Next, I will introduce the 2 classical algorithms, namely ranking and water filling. Those algorithms were originally studied in the online bipartite matching problem and proved them to be optimal. We adapted the 2 algorithms to the fully online model in our earlier work. Finally, it comes to our contribution, beating the classical algorithms. Previously, we have shown tight ratios of the 2 algorithms, and in this work, we proved that the 2 algorithms are no longer optimal in the fully online model. Let's move on to the model. So in the fully online matching problem, there is an underlying graph, but at the beginning, we have no information of the graph. There are 2 types of time steps, arrival of a vertex. On the arrival of a vertex, we see the edges between the newly arrived vertex and all previous vertices. Here, I use blue to denote the arrival of a vertex. The second time step is a deadline of a vertex. It means this is the last time a vertex can be matched if it's not matched yet. So here, the left bottom vertex in red reaches its deadline, and we have to make matching decisions now. There are 3 options. Let's say we match it to the second. So on and so forth. More vertices arrive in the graph, and some vertex reaches the deadline, and we make matching decisions. This is an online algorithms. All matching decisions are irrevocable. So the objective is to maximize the size of the matching. So in this run, our algorithms matches 3 edges, and the optimal, in hindsight, which knows the full graph, sees the perfect matching. So the optimal is size 4. So we say the competitive ratio of this algorithm is 3/4. We made a crucial assumption in our model. We say that all neighbors of V must arrive before V's deadline. Just imagine each vertex is active in the graph between its arrival and its deadline. Then we are saying that all neighbors must have overlapping time windows. This assumption is important. And as I mentioned before, this is a generalization of the online bipartite matching problem. In the online bipartite matching problem, there is a bipartite graph, one side of the graph being offline and the other side is online. So just imagine offline vertices all arrive at the beginning and have deadlines at the end, and all online vertices have deadlines right after their arrivals. In this way, fully online matching is a generalization of this online bipartite matching. A simple observation gives that any greedy algorithm is half competitive. When I say greedy algorithm, I mean when for each vertex, if there is an edge available, then we never give up this vertex. So the main question in this line of research is focused on how to design algorithms with competitive ratio better than half. Now let's move to the second part of the talk. So ranking, let me start with ranking. Ranking was originally proposed by Karp, Vazirani, and Vazirani in online bipartite matching. And we first draw a random permutation over all offline vertices. Then, on the arrival of an online vertex, we match it to the first unmatched neighbor according to this permutation. This algorithm is adapted to the fully online matching problem. Instead of drawing a permutation over all offline vertices, we draw a random permutation over all vertices, simply because all vertices are online in the fully online model. And we make the algorithm lazy, meaning that we only match vertices on the deadline of some vertex. Then on the deadline of a vertex, if it's not matched yet, we will match it to the first unmatched neighbor. Let me give you an example. On the arrival of a vertex, we draw a rank YV uniformly from 0 and 1, independently for each vertex. And as you can see, if we order the ranks from small to the largest, this is equivalent to draw a random permutation over all vertices. Then on deadline of V, we just match it to the neighbor with the smallest rank. Ranking is a randomized algorithm. Naturally, we evaluate its performance by the expected size of the matching it produced. Ranking is shown to be 1 minus 1 over E competitive for online bipartite matching, and this is optimal. And it is 0.567 omega constant competitive for the fully online bipartite matching. And this is shown to be tight. So when I say tight, I mean there exists an instance in which ranking only matches omega times the optimal. And for general graphs, ranking is shown to be 0.521 competitive. These are proved in earlier work. Next, let's look at water filling. This works for the fractional version of the online bipartite matching problem. In the fractional version, we are allowed to match edges fractionally. So in the online bipartite matching setting, on the arrival of an online vertex, we match it continuously to the least matched offline neighbor until the online vertex is fully matched or all its neighbors are fully matched. So the name water filling comes from the following concept: water level of a vertex. It simply means the matched portion of a vertex. In this language, we match an online vertex continuously to the offline neighbor with lowest water level. This is also adapted in the fully online model. Again, our algorithm is lazy. On deadline of a vertex, we match it continuously to the least matched neighbor, or the neighbor with the lowest water level. Again, let me give an example. So on deadline of this vertex, all the 3 neighbors have currently water level 0. I will increase them continuously and in a balanced way, because I will always choose the one with the lowest water level. So it will end up with 1/3, 1/3, 1/3. Later, the right top vertex reaches its deadline, and 1/3 of itself is already matched. So there are 2/3 to go. So you end up with myself being fully matched and the 2 neighbors are matched 1/3. Water filling is shown to be 1 minus 1 over E competitive for fractional online bipartite matching. Again, this is optimal. And water filling is shown to be 2 minus square root 2 competitive for fractional fully online matching. Again, this is tight. Here is a table summarizing the previous works on this line of research. So there are 2 important algorithms: ranking for the integral version of this problem and a water filling for fractional version. As you can see, ranking and water filling are optimal in the online bipartite matching setting. And when generalized to fully online matching, we have characterized the tight competitive ratios of these 2 algorithms. So the main question we study in this paper are, can we do better than the 2 classical algorithms? Are ranking and water filling optimal in the fully online model? So here are our results. We provide 2 algorithms, balanced ranking and eager water filling. they have competitive ratios 0.569 and 0.592 respectively. So we answered the previous question affirmatively. So the improvement of the ratios are not that large, but the design of our algorithm are very intuitive and interesting. And in the rest of my talk, I'm going to focus on the design of our algorithms. Before that, let me give an economic view of ranking and water feeling. This also explains our this will later be used to explain our intuition for designing the new algorithms. So we fix the increasing function g from 0, 1 to 0, 1. Then for each vertex, we set the price of them to be g of y of v. Here, yv is the rank of a vertex. And in this way, the vertex with the smallest rank corresponds to the vertex with the lowest price, or the cheapest vertex. Imagine the vertex reaches its deadline u is a selfish agent. If it picks the neighbor with some certain price, its only utility will be 1 minus the price. So ranking simply says u will pick the vertex with the smallest rank, and this introduces a natural gain sharing process between the two vertices. So basically, u pays the price gy of v, so v got gy of v, and u got 1 minus gy of v. And this gain sharing process is highly tied to the randomized primal due framework for analyzing ranking. So basically, if you want to show ranking is alpha competitive, it suffices to show that the expected gain for each pair of neighbors u and v, alpha u plus alpha v in expectation is at least alpha. I'm not going to expand this further, but this is how we prove the competitive ratios of the algorithm. And this is also the framework in our paper. So for water feeling, this is similar. I use f instead of g to denote another function, but again, it's also an increasing function. Now the price of a vertex is f of xv. So x of v denote the water level of vertex v. Again, the lowest water level corresponds to the cheapest vertex. Remember that we match vertices continuously. So when u matches v by an epsilon fraction, we're going to share the gain that alpha v takes fxv times epsilon and alpha u times 1 minus fxv times epsilon. And after this step, you see v will raises its price from f 0.1/3 to f 0.1/3 plus epsilon. And here, water feeling is no longer randomized. So the primal due analysis says that if you want to show water feeling is alpha competitive, it suffices to show that the expected gain alpha u plus alpha v is at least alpha. So now it comes to our algorithm, balance ranking. Our intuition is quite simple. Since water feeling has a better competitive ratio than ranking, so why don't we use water feeling to correct the decisions by ranking? So we introduced the following combination of water feeling and the ranking. We set a price of each vertex v to be gy of v plus fx of v, where yv is the rank of vertex v, is a random number, and x of v denote the water level of v, the probability of that v is matched. Then, on the deadline of each vertex, we match it to the neighbor with the lowest price. So if we set the function f to be all zero function, then this is equivalent to ranking. So we are degenerated to the ranking algorithm. So one might wonder, how do we define x of v? So a straightforward way is to define XV as the beforehand water level. So at use deadline, X of V will simply equals the probability V is matched before use deadline, where the probability comes from the random decisions of our algorithm. However, we're not going to use this. This is crucial to our analysis. We use lookahead water level, meaning that at use deadline, we define XV to be the probability V is matched after use deadline. So in other words, we want at use deadline, we want to predict the look ahead water level of all its neighbors. And it's not even clear why this is a well-defined algorithm. So one of the crucial lemma in our paper says that balanced ranking is well-defined and it can be computed efficiently when F and G satisfy some Lipschitz constraints. I'm not going to prove this lemma in this talk, rather I'm going to give an example. For simplicity, I'm assuming gy equals y over 2 and fx equals x over 2. There are 3 vertices in the graph and the bottom vertex reaches its deadline. We want to predict what will happen after its deadline. So it's easy in this case because the 2 neighbors are symmetric. So with half probability, the first one will be matched, and with half probability, the second one be matched. Together with their ranks, the first vertex has a smaller price, so it matches the first one. Things getting more complicated when this new vertex reaches its deadline, and we want to calculate x2 and x3. Let's look at x2 first. This vertex is matched either in the deadline of the previous vertex or at the current round. So in the previous round, it has a smaller price if and only if y2 is smaller than y1. Here, y are the ranks of these vertices. Or it has a smaller price in this round compared to the third vertex. This happens when y2 plus x2 is smaller than y3 plus x3, according to the definition of G and F. Similarly, we can write down the constraint for the third vertex, which is the second equation on the left. If you trust my calculation, this gives x2 roughly equals 0.708 and x3 roughly equals 0.792. Together with their ranks, we see that the second vertex has a smaller price and it will be matched. So given this lemma in hand, the rest of analysis goes in the following way. So we want to analyze the expected gain of alpha u plus alpha v. And we're going to split the gain into 2 parts, those related to G part and those related to the F part. As would you expect, the G part, this analysis is similar to those of ranking. And the second part, the gain of V, a gain of F, will be similar to those analysis of water feeling. And then finally, we related 2 bounds. Thanks to the lemma, we can leave the optimization of f and g to the last step and to optimize our competitive ratio. I haven't explained why we want look ahead water level instead of beforehand water level. And this is highly related to the analysis of the gain of F part. And I will try to give intuition in one slide. So for each vertex V, we know its water level grows from 0. And we assume that after the deadline of the first vertex, its water level grows to xv1. After the deadline of the second vertex, it grows to xv2, so on and so forth. So now let's consider the gain of V corresponding to the F part. At the deadline of the ith vertex, the price of V will be fxv of I. And if we use beforehand water level. And by definition, and the probability V is matched to the I plus 1's vertex will be XVI plus 1 minus XVI. So the expected gain will basically be the summation of this thing. And if we use lookahead water level, then the price will be larger, right? On the deadline of on deadline of vertex I plus 1, the price will be FXVI plus 1. So the only difference is the superscript. It differs by 1. However, when you look at the worst case of these two formulas, the first one gives XVN times F0. Basically, in the worst case what happens when XV1, XV2 all equals to 0, and it suddenly jumps from XVN minus 1 to XVN. However, if we use lookahead water level, according to the monotonicity of function f, this formula is at least the interpretation from 0 to xvn fx dx. So the second bound is much better than the first one, and this is important for our analysis to go through. Okay, that's enough for the balance ranking. Now let me tell our design of eager water filling. Recall that if you actively match V, when I say active, I mean you would like to pay the price fx of V. If this happens, the utility of U, the gain of U, would be 1 minus fx of V. And if you sit and wait for some other vertices to match myself, then my gain will be fx of U. So our intuition is like, if x of fxv plus fxu is at most 1, then why would you wait until its deadline? And this gives the algorithm eager water filling. The eager corresponds to the first part. The first step, upon the arrival of a vertex u, we continuously matches the neighbor with lowest water level if fxu plus fxv is at most 1. And then in the second step, at the deadline of each vertex, if it's not fully matched, we continuously match it to the neighbor with lowest water level. I would like to remark that water filling is only uses the second step. So actually, water filling ignores the information of the edges among the vertices that have arrived but have not yet reached the deadlines. And it is observed that water filling is actually optimal in this harder model if we don't see those edges. I would like to say that our eager water filling utilized this information by partially matched vertex on their arrivals. We proved that eager water filling is 0.592 competitive, and it shows the separation between the fully online matching problem studied in our paper and the general vertex arrival model by Huang due to an earlier upper bound of 0.5914 by Gavin et al. Let me summarize our work by a slide of future work. So some immediate question would be to give tight competitor ratios of the fully online matching model. Apart from that, there are some other immediate questions raised from our work. The first one is, balance ranking is a well-defined algorithm even when G function corresponding to the ranking part is only between 0 and epsilon. But how do we analyze these algorithms? Intuitively, this is closer to water filling because G only plays a tiny role in this algorithm. So in our work, G is going to be the major part, and F is relatively small. And we don't know, the difficulty is that we don't know how to analyze this algorithm, and we wonder if this can match the competitive ratio of water filling in an integral way. The second question is about, what about eager ranking? When I say eager ranking, I mean match on arrivals if gy of u plus gy of v is at most 1. And it is observed that the same hard instance for ranking the eager ranking algorithm does not beat omega constant for any function of g. But what about combined balance ranking and eat-your water filling together? Is it possible to get a better bond? That's all. Thank you.